seamless in operation. We have a bunch of sensors, which again, I said, we developed most of those sensors in the house because you cannot find COTS devices. Even if you find the COTS devices, end up being very expensive for 26 joints. So 26 joints times, motor controllers times, sensors like a load cell, which doesn't actually exist in the industry. So there's a lot of internal development and kind of putting this in a production mode. Some basic, so we have 6 load cells, force moment sensors, 2 on the feet, 2 on the pelvis and torso, and 2 in the hands. So how you engage with the robot is really projecting your sort of reflection, or force moment reflection, to what you ask your robot to do. So sometimes when you're lifting the heavy load, you apply more pressure on that sensor that's sitting on the hands, which is actually transformed back into the Jacobians, back into the commanded torque that goes into joints. Initially, we had a very limited space on that hardware that sits on the joints in terms of what type of low-level controllers you can implement. So basic PD was really used, which doesn't really give you really high bandwidth of actuation, which is required to provide this smooth motion. So we changed this recently into still linear, but at least optimization-based control. So low-level joints operate now almost to 20 hertz, which is really, really good, using H-infinity controllers, which helps you also compensate for backlash and friction. So that's kind of low level. Middle level is really probably what would be mostly interesting, but if you don't solve the problem at the low level, you run into issues that you cannot execute what you're commanding for middle level or high level. So having this sort of low-level controller solved to compensate all the nonlinearities while still being relatively linear and easy to input on hardware was a key component. So some of the basic stuff that we patented a long time ago is really what we call get-out-of-way control, which is basically, I want to achieve 0 force and 0 moment applied to human. That's my goal. And how do I do this? Through the Jacobian transpose of the end effector, you can go back into the basic principle to command the torque that will allow you to sustain that weight of the robot, compensate for the gravity as well as the payload, and actually achieve that sort of fluentness in motion. I kind of mentioned some of the characteristics. We tested a bunch of stuff. 3 miles per hour unloaded and loaded is pretty good speed, especially in the industrial environments. Nobody wants to really run in there. So you're moving relatively slowly, especially with the load applied. So in some of the situations when we have the exoskeleton, because we have 2 battery packs in the back, and those batteries run about 90 minutes per workload. So they're what we call hot swappable. So somebody in the back will have to come back and swap this battery. Unless you want to basically shut down, step out, do all the stuff from the beginning, which is time consuming. So one thought was, why don't we just simply make this autonomous? So let's the user step out, exoskeleton self-stabilizes, and users just simply replaces the battery and then steps back, which makes sense because then you reduce the number of people servicing that thing. And in industry, everything is about reducing the number of people working if you have a robot. They can be in supporting roles, but taking a few people from that sort of work is the sort of return on investment for some of the industry aspects. So the next option for the exoskeleton, sometimes you're going to work in dangerous environment. So being able to let that exoskeleton into hazardous environment without a human also makes sense to do sort of autonomously. But again, machine is designed not to be humanoid. Machine is designed to be exoskeleton / possibly humanoid. So there's a lot of issues with kinematics that we have to resolve in order to make this sort of humanoid-like robot. And so that by itself is a fairly significant challenge. So, I kind of just break it down again the controls into high level, mid level, low level, and sort of motor controllers, which, unfortunately we had to also design firmware for that, which was a little bit silly, but again, spending like, $1,500 for Ingenia or for the elbow drives is expensive for 26 joints. So the key part of high level is really that human intent. And each user projects forces differently. More experienced one is very easy with machine. Less experience is actually almost afraid of the machine itself because you're bearing this thing. And like first time driving, you have a tendency to hold that wheel really, really hard. So projecting unnecessary force and momentum on the wheel. So the same happens when you first time step in there. You feel nervous as you're pushing force moments harder, which basically translates into the pumping more torque, which is unnecessary. But one aspect of the really understanding the human intent is really you have an understanding of human intent through measurement of those forces and moments coming from 6 places. So there's a bunch of stuff that we did in terms of probabilistic machine learning, in terms of some level of reasoning. It's very hard to model human intent. So can we actually learn that transition from the data that we collect? And that allows us to be agnostic to users. So you don't have to be retuning your controllers depending on the who steps in there. So that saves time again and becomes kind of more agnostic to the people that operate. Also improves the safety. And safety in exoskeleton is an issue, but you can address this mechanically by protection, but then it becomes a silly machine. And you don't want to wear the cage around yourself by walking this thing. But also you can solve this by controls and better sensors. So as a result of that, we kind of went through these sort of basic controls. Then we also established optimization-based control, which I'm sure all of you know what that is. It's a basically hierarchical task-based controller which kind of works simultaneously without traditional controls. So we can prioritize tasks in terms of, for example, balancing is a key moment. The other one is really contact with your feet that has to be ensured, and then all other tasks becomes kind of secondary because doing something with hands is easier to sort of prioritize or schedule as opposed like guaranteeing balancing and contact. So kind of combination of those traditional controls and optimization-based controls kind of gave us really significant improvement compared to the original exoskeleton. So I'm going to play a few videos because I think the words, the pictures say much more than my words. So that's kind of how it looks like. It's a little bit awkward to walk. You still execute what you need to do it, but you do it slower, and turning is especially the key here. Does happen in 5 steps, for example. This is off tether, but because of safety in the office, we have to have a gantry. So now if you do the same motion with this sort of a combination of optimization-based controllers and traditional ones, you see that motion is much more fluid, and especially turning around happens in 3 steps, which is pretty good for like novel user in this case. We do evaluation of quantitative metrics. Gait, human gait is very important. We can also do measurement of muscles and EMGs. So that also gives us indication how well do we do in controls. Because if you're straining your muscle, but perhaps you're walking smoother, that doesn't play well. Because somebody's going to get injured, basically kind of carry this sort of load. This is another sort of important test in sort of side steps. Again, you see it's a little bit not fluid as we would like to be. And if I had to go down here with the new sort of control techniques, this is what happens. So this is all running on a hardware that actually exists on the back of the exoskeleton. It's an x86 processor, and we also use NVIDIA Orin to kind of complement those functions. So everything is running on a constrained hardware, not off the computer itself. And then if you do this with the load, you kind of see fluency as well. This is an 80-pound suitcase, which feels about, I think, 8 pounds that you're carrying. So significant reduction in sort of what you feel in the robot itself. In this case, 7 steps by turning. This is critical in the apron application, which is the tarmac of the airport. Turning around, putting the bags is a really critical operation. So if you can do this smoother, then that's gonna key, because it looks also safer as well. So you can see that smoothness of motion in this case. It's fun actually being the suit. It's I did it like 3 years ago, and then first time I noticed like backlash is here, friction is there. It's like get rid of this stuff because you can improve a bunch of stuff. And I just recently stepped with the same new controllers, and it was like I felt like you can really start running. Not that you want to run, but in any case. So practical implementation of something that we theoretically kind of implement and play with, but this is also kind of how we're taking this sort of research and development and putting it into sort of commercial use, which is, I think, is a neat example. I don't know about it with the lifting of 200 pounds, which is really neat. I think that's probably the heaviest load that any exoskeleton or humanoid can lift. It's not like like you can lift before you start to overheat the motors, but in any case, some instantaneous motion of 200 pounds is required. Especially if you're pushing, that's even more desirable. So all these use cases come really from the customer that we face, or investors, including big companies like Caterpillar, which are using all these heavy tools to manipulate on the factory floors. Okay, so maybe now it's to the more interesting side. So how about if we, the reason I mentioned replacing a battery is also hazardous environment. Can we do this in an autonomous way? So going back, this is balancing under disturbances. Again, this combination of optimization-based control, task prioritization, pretty robust off the tether. The one video that I cannot play on my machine because on Apple is this. And now you have kind of task prioritization. You're still balancing yourself while handling load. In this case, we're just kind of playing goofy stuff and juggling these two 40 pounds loads. But it's actually pretty impressive how your momentum controller is changing center of gravity to compensate for that sort of establishing balance and keeping the feet on the ground. What we are currently working, I think, is the key is continue to make movement or steps with the robot. The things that work in simulation, as is great in simulation. But right now we are working actually with Aaron's lab and a few other universities to help us actually speed up some of the development. Theoretically, it should be working, but we are not there yet. So let me just quickly switch. This is actually also neat for implementation. So we do a lot of teleoperation because teleoperation can actually quickly get you where you need to do what you need to do in manipulation. No pre-programming. You can actually get much quickly with teleoperation in execution of certain tasks. So we build what's called magnetic motion tracker that either tracks your controls in a task space, or you can also do in joint space. We do geometric retargeting to avoid self-collision with the arms and the torso. And then in this case, it's running while optimization-based controller is stabilizing the things. The teleoperation by Eric here is used to handle this load. And this is 100 pounds load, which for our applications, humanoid needs to handle at least that much because that's what the industry requires. Not handling like empty boxes or not handling some light objects, but something that's actually meaningful. Because I'm running out of time, I'm gonna not play this video. And I want to just give you some indications of the new robot that we just finished, which is going also to production, which this 16 degrees of freedom anthropomorphic robot, and you can actually do quite a bit kinematic equivalent tasks. This is sort of silly, but actually this task on the right is really what you would need to do in kind of hazardous environments. Let me flip through that.
It's a pure roll.
Yeah, so this is still, you can still make an exoskeleton as long as you attach the load cells on the bottom. Yes. So you can, but in this case, we decided to take human completely out of hardways. Yeah. And the application was really a repairing of the power lines. So you have to have you don't want to have a human there, that's the whole purpose. Yeah. So that dexterity gives you full kind of human motion, from 7 degrees of freedom that are kinematically. So now you can actually teach the robot to repair some of the tasks and actually put the kind of load controls. Okay, so I think you can, it's 100 pounds. There's a set of cameras on the top, so you can actually use that for autonomy or to send information back to the teleoperator who's wearing the goggles and so on. The key here is really that you're not replacing the workforce, but you're allowing more exciting people to come into the place of very sort of traditional jobs. Like, for example, vegetation management down here. Workforce is actually getting old and nobody wants to do vegetation management. Even though they're arborists, they have to have the skills. But allowing like this, 60-year-old man wearing like, cool goggles with wire controllers doing this on the ground and cutting the trees without being like, endangered is the key. And that same applies for everybody because putting somebody here on the boom on like, 10, 20 feet is dangerous. Okay, I don't have anything. I think I may be on time. A little bit over time, but. Well, thank you. Any questions? Yes.
Yeah, so I love being some optimization-based, prioritized control. That's great. How is that being prioritized? Is that a strict prioritization?
Yeah, so right now we set up strict prioritization. So stabilize first, then do the contact, constraint, and then do something else.
So it will just ignore the lower priority tasks entirely.
Yes.
Before you take the other one. So it's got like some balance of the costs that's trying to mitigate.
Because safety is the key here.
Right.
And I want to make sure that whoever is inside that robot is safe and stability is guaranteed to the.
I totally agree with that. I think it's a great way to go. Does that mean just in effect that, like, let's say you have something that you're holding and that's going to threaten the balance? Is it going to like let go? Is it going to?
It's going to try to compensate first. So you can see actually when the human is in there, you're basically moving your center of gravity, you compensate this automatically. And essentially, I didn't show like when you look at the side picture of the exoskeleton lifting that box of 100 pounds, you will see that your CRG is changing because that's your first constraint, right? To compensate for it, to get a polygon on the foot above the CRG.
So does that mean that you haven't even noticed any switching issues when you go from constraints are satisfied to constraints are not quite satisfied? You see like a jerky jerk in the control?
Because we combined with our previous version, which is still this what we call get out of A, you basically just having you want to apply always zero force in the hands. That's your goal, to human to feel zero force, 0 moments. So that controller is already kind of smoothing that transition between the optimization controller. And it's running actually a high frequency rate because we cannot get optimization base to run more than 350 Hertz, which is still good. But right program running on that constrained hardware is a pretty good that speed. But our overall controls work at 1000 Hertz. So you have that kind of switching is compensated for the controller that's running higher. Yeah, no problem. Yes?
Similar question about what are you doing with the intent, human intent?
So
is it a finite state machine, or are you setting trajectories for your reference points, or? So
the intent is captured to the gate. So you can actually predict the gate of the user across many users, then you are actually capturing that intent properly. So you can use probabilistic models that are based on a HMS or HSM. So you can actually, because we have a bunch of training data going on, every